In this Level 2 course, you'll learn about diesel fuel cleanliness. You'll also learn the causes of premature injector wear and failure and how to prevent damage to the injector system. When you've completed this course, you'll have learned important fuel system terminology to help with your understanding. You'll study the role of diesel fuel and fuel cleanliness, including how fuel cleanliness is measured and what standards are used. You'll also learn about the causes of premature injector wear and failure, and how wear and failure can be prevented. Finally, you'll be introduced to several products specifically designed to prevent premature wear and failure in the fuel injector system. Let's begin by learning some fuel system terminology. We'll go into more detail on some of these terms later, but let's start with a basic understanding. When discussing fuel injection systems, FIE represents the fuel injection equipment. Cummins engines use HPCR, or high-pressure common rail systems, in their engines. 1 micron is 1/1,000,000th of a meter, or 394/100,000th of an inch. In the illustration shown, you can see that a bacterium is 2 microns in diameter, a red blood cell is 8 microns in diameter, and the white blood cell is 25 microns in diameter. The smallest particle that can be seen by the human eye is 40 microns, which is also the largest particle that can pass through a Fleetguard full-flow lube filter. By comparison, a human hair with its 50 micron diameter seems gigantic and has the potential for real harm if it enters a fuel injector system. The latest industry standard ISO definition of particle size is a micron. Under ISO 4402, the only performance data a manufacturer had to provide about a filter was based on its ability to remove 10 micron particles, or those particles approximately the diameter of a human hair. ISO 11171 calls for multi-pass testing across a wide size range. The process provides more accurate readings across the critical region, the difference being greatest at exactly the sizes of concern for fuel systems. HPCR fuel systems consist of a fuel pump supplying clean fuel that is passed through the fuel filter into a high-pressure common rail, HPCR, feeding individual injectors. The system is governed by the engine control mechanism, ECM, which opens each injector electronically. Fuel exits through the drain line. Cummins engines use HPCR fuel systems. These systems have fuel injection pressures ranging from 25,000 psi, 1,723 bar, to 30,000 psi, 2,067 bar. At these pressures, any particulates in the fuel are like taking a sandblaster to the internal precision parts. A basic schematic of the fuel injection equipment, FIE system, is shown here. Diesel fuel has 3 main roles in the system. First, it provides power to the engine. Second, it acts as a lubricant as it moves through the FIE system. Finally, it acts as a coolant by removing heat from the FIE system. The importance of clean fuel in HPCR systems can't be overstated. There are many types of fuel contamination. The first one we'll discuss is water. Water can be present in the FIE system either as freestanding water, which means it has not entrained or become mixed with the fuel, or as emulsified water, where it has become entrained in the fuel. The illustrations to the right show the difference between free and emulsified water. Water in the FIE system can cause reduced equipment or filter life when microorganisms develop or when rust or corrosion develop. Also, water adversely affects the lubricity of the fuel, which we'll discuss in a minute. If water enters the FIE system, it can flash when exposed to high temperatures, causing a rapid increase in pressure and possibly blowing the tip off the injector. As you've learned, water affects the lubricity of the fuel. If it is reduced sufficiently, it can cause wear in the equipment. If water is present, rust is evident in the fuel filter and system components. There are 2 main types of fuel contamination, organic and inorganic. Asphaltenes are tar-like organic contaminants that are inherent in the crude oil used to make diesel fuel. These substances cause buildup that can prematurely plug fuel filters. Inorganic contaminants can include dirt and rust, or metal from components. These particles are the most damaging to fuel injection equipment, FIE. Inorganic contaminants like dirt, rust, and metal are the leading cause of premature injector failure. The slide to the right shows a microscopic view of inorganic contaminants in diesel fuel. Inorganic contaminants can be introduced to the system from poor quality fuel sources or from the operating environment. For example, when a truck is running in a very dusty or dirty environment. These contaminants cause premature wear within the fuel system and can lead to fuel system component failure. Fuel injectors can be easily damaged if they are exposed to debris in the fuel, and severe erosive wear, similar to the effects of sandblasting of the other components, is also possible. Contaminated fuel can either cause erosion to occur or to accelerate wear that has been initiated by some other mechanism. In the photo shown below, you can see erosion grooves caused by inorganic matter in the fuel. To the right, you can see how a human hair is far larger than the fuel system clearance of 3 to 5 microns, creating the potential for wear. If contaminated fuel is being used, typically you would expect to see fuel injectors fail prematurely and erosive wear in the equipment. The illustration below shows a standard fuel injector. The magnified slide to the left shows erosive wear on the outer edges of the control valve where hard particles in the fuel have caused damage. So, how is the cleanliness of fuel measured? The International Organization for Standardization, ISO, issued a set of guidelines, ISO 4406, also called the ISO Cleanliness Code for fuel cleanliness. To the left, you see the chart for the ISO 4406 code. The standard uses 3 major particle sizes: particles larger than 4 microns, particles larger than 6 microns, and particles larger than 14 microns. The particle counts are typically specified in units of particle per 100 milliliters of fluid. Looking at the chart, you can see the 3 valves. However, the critical sizes with regard to injector wear are 4 microns and 6 microns. Now that you understand ISO 4406 standard, take a look at the overall cleanliness levels shown in the chart. High-pressure common rail HPCR systems require extremely clean fuel with an ISO 4406 12996 cleanliness level, as shown in green on the chart. Using the particle size illustration described earlier, let's see what the ISO 4406 12996 standard means. Per 100 milliliter fluid sample, 12 represents fuel containing up to 4,000 particles larger than 4 microns, or the smallest particle in the critical region. 9 represents fuel containing up to 500 particles larger than 6 microns, or slightly larger than the largest particle in the critical region. And 6 represents fuel containing up to 65 particles larger than 14 microns, slightly larger than the largest particle shown. With this understanding of the importance of using only the cleanest possible fuel in FIE systems, let's look again at the causes of premature injector wear and failure. Today's fuel systems operate at a much higher pressure than older systems. Higher injection pressures and smaller clearances make today's injector components highly susceptible to premature wear from inorganic contaminants. It is vital that rust, dirt, and metal particulates be removed from the fuel before it enters these precision systems. Failure to properly filter the fuel of inorganic contaminants leads to premature injector wear and failure. It is critical to filter out dirt, rust, and metal at the critical particle sizes of 4 microns and 6 microns. There are 3 elements of contaminant removal in fuel. First is fuel island filtration, where contaminants originating in fuel storage and/or transfer tanks are filtered out. Second is the primary remote mount fuel filtration. This system is usually mounted on the suction side of the fuel system. It removes contaminants prior to fuel reaching the fuel pump. Finally, there is the secondary engine-mounted fuel filtration. The system is usually mounted on the pressure side of the fuel system and removes finer contaminants to further protect the injector system. Using all 3 filtration methods is the best way to reduce or eliminate premature injector wear and failure. Now, let's discuss the specific products Cummins Filtration provides to protect sensitive FIE systems. The FleetGuard FF5782 is a new filter introduced for secondary fuel filtration. The NanoNet media delivers clean fuel to meet ISO 12996 as long as the incoming fuel meets ISO 18163. NanoNet media removes up to 10 times more contaminants than the leading competitive product and is so superior in removing harmful contaminants that Cummins Filtration uses beta to measure the product's performance. This filter has a B4 rating of 1000 and features a filter-in filter design. The NanoNet media prevents premature injector wear that can lead to injector failure, and when injector equipment performs as it was designed to do, total cost of ownership, TCO, is reduced. We've discussed the importance of fuel island filtration. The fuel regen is the first line of defense for hard particle removal. Typical bulk fuel storage cleanliness levels, when measured by ISO standards, do not provide the cleanliness levels required to meet fuel injection equipment FIE manufacturer's standards. The fuel regen system helps achieve an acceptable 18163 ISO standard as required by fuel manufacturers, thus reducing the high replacement cost for critical parts such as the fuel pump and injectors on HHP engines, and reducing fuel system wear and maintenance over the life of the engine. Adding the fuel regen system to a bulk fuel storage tank will result in increased uptime and operational efficiency at job sites. Cummins Filtration offers several industry standout solutions for primary remote mount fuel filtration systems. These products provide exceptional performance. The Diesel Pro, Fuel Pro, and Industrial Pro all achieve 95% fuel-water separation per SAEJ 1488. They all feature seeing is believing technology that indicates when not to change a filter and have easy-to-change filters for a 5-minute filter change. All of these units can be primed through the top port, so no priming pumps are required, and the filter elements for these units feature Stratapore media for exceptional filtration. Depending on the unit, some of the options and configurations include water in fuel (WIF) sensors, heaters including preheaters, fluid and overnight heaters, and clear bottom bowls with drains. Now that you've completed the Level 2 Fleet School module on fuel cleanliness and premature injector failure, you should know the types of fuel contamination and their effect on fuel injection equipment, FIE system. You should be familiar with the industry standards and system requirements for fuel cleanliness. You should also understand the causes and of premature injection wear and failure and how to prevent it. And you should be acquainted with the FleetGuard products designed to prevent premature wear.